All right, so the reason, ooh, I misspelled that. That's what happens when you type so fast. All right, so the reason why I have organized things the way I have, if you guys remember, we started with types of solids. We took a break from types of solids. We did Lewis structures, shapes, and polarities, and now we're going back to types of solids. The reason why is because the covalent molecular solids are made up of things that are molecules, which you use Lewis structures to figure out anyway. So that's why I wanted to do it in that order. With the covalent molecular solids, the things that are likely to come up are obviously going to be referring to things molecular-wise when it comes to their the polarity, because that's going to influence things like their melting and boiling point. It's going to also influence things such as solubility. So just to kind of recap, when we're thinking about our types of solids, they often ask about certain types of solids because they have certain properties, and then they use them as compare and contrast. So when we are talking about our covalent moleculars, properties that they often tie to this question are going to be explaining its melting and boiling point, the reason why is because these ones obviously have very low ones. So when we are thinking about this guy here, I'll let you guys get that down before I move it real quickly. So covalent molecular solids, they're often going to ask you to explain their property of why they have a low melting and boiling point. The reason why is because these guys are different from all the other solids in that condition. So all these other solids tend to have higher melting and boiling points because we are trying to break intramolecular bonds. We are trying to break bonds that are quite strong. For the covalent molecular, the solid that holds together a water, say like ice, for example, is these intermolecular forces, not these bonds here. So these bonds are really easy to break, and thus it has a lower melting and boiling point. And that's what you see consistently throughout the covalent moleculars. All right. So in order for these guys to change state, you need to break this bond here and only this bond. You don't have to break these bonds here. If we broke these bonds here, we have a chemical reaction occurring because now we're changing what we have molecularly. But these guys all over here tend to have higher melting and boiling points because these are now intramolecular forces. They require more energy to break, thus higher melting and boiling points. If you were to rank them, covalent molecular are the lowest. Ionic and metallic are kind of middle ground with each other. Maybe metals are a little bit lower than ionic, but it's not a huge difference. They're going to be fairly middle ground. And then the highest will be the covalent networks because they have covalent bonds that need to be broken in order to change phase. All right. The only exception to that is the 1D covalent networks, which they're very unlikely to ask you because they're only being held together by the intermoleculars as well. So basically it's null. We're talking 2D and 3D. Are we okay with that? The other thing they like to ask with the covalent molecular is solubility. So we're talking about the ability of something to dissolve or mix together. In this case, it's going to depend on the polarity. So like dissolves with like. So nonpolar with nonpolar. And polar with polar. So like with like. So the reason why, if I had a polar molecule and I was trying to dissolve it into a non-polar molecule, polar molecules such as water, I cannot dissolve into something like oil, which is non-polar, because we are talking about something that is charged, trying to mix with something that's uncharged. So there's no way for them to mix together because of those two different things. If I have two non-polar things, then we can actually align the positive and the negatives together, so that way they can actually mix together. If I had two non-polars together, they can again also mix together because they're all kind of in the same boat. Are we okay with that? So that's commonly what comes up as the covalent network ones. When we are talking about things like ionic, they will often do the solubility question as well. So you will often see covalent molecular and ionics paired together in a solubility-based question. In this case of the solubility, we are talking about how the positive ions and the negative ions are attracted to the water molecule. So positive ions will be attracted to the negative part of the water molecule, and negative ions will be attracted to the positive part of the water molecule. So just be careful when you're explaining something. So if I have a positive ion here, the water molecule is going to orient itself so that way the slightly negative oxygen is isolating it. The reverse happens if I have a negative ion. The water molecule goes in the other direction, where you have the slightly positive bit aligning with the negative. So that's why that's dissolving. So again, they like to pair that question in there. With the ionic solids, they often like to pair in brittle and explain why it's brittle. Again, you can go back to the lessons from the start of the year to find that one out. They often also like to ask about electrical conductivity. Which is no in the solid form, but yes if you are aqueous or if you're molten. So you're able to move those ions around. So they often like those questions there. Let's move this down. Just mindful of our time. Questions so far? It's basically like a recap of everything we've done for types of solids. I know a lot of this is going to be really rusty because we did this like as our first couple lessons. They are still on Google Classroom and Google Sites, so you can always backtrack and learn them. So the answer, it will not be conductive if the ionic solid's in a solid state. It will be conductive if it's aqueous, so that's dissolved in water, or if it's molten. They might stick in covalent moleculars for electrical conductivity, and the answer is no, because again, it doesn't have a charged particle that's moving. But I'm just trying to highlight things that are positives that they'll normally kind of pull out. They could obviously ask any combination, but in that case, you're going to have a null. So electrical conductivity for covalent molecular is not, because it doesn't have a charged particle. These are only slightly charged, and being slightly charged is not enough to carry an electrical charge. You also have your metals. Often with the metals, they like to, again, talk about electrical conductivity. It would help if I can spell conductivity correctly. It's been misspelling all day. The other thing they like to ask with the metals is the fact that it is malleable. So if I hit it, it'll change shape and still like hold together. Brittle means if I hit it, it's going to smash apart. Now I got to figure out how to spell malleability. There's only so many words in my brain. There we go. Thank you, Google. Malleability. They could also ask about ductility, which is just being able to pull it into a wire, but more often they ask about, I'll put ductility in there. Ductility, there we go. It just means that it can change shape. So those are the common things they ask in regards to metals. They could also, again, ask and say, oh, metals are not soluble. Why are metals not soluble? Well, again, it's going to be the metallic bond is strong, and it's not going to interact with water. The attraction to water will not allow it to break apart. So when we're thinking about solubility, another common thing to think about is it more attracted to itself or more attracted to the substance it's trying to dissolve? And the last one then is your covalent networks. With the covalent networks, they often ask about high melting point, high boiling point. I'm having all issues today. So that's usually what comes up with it. But again, it could tie into electrical conductivity. In fact, the 2D, the graphene, is electrically conductive. So that's the other thing that might come up with covalent networks. But again, remember that's only the 2D. A piece of advice for you guys is that from my experience of my many, many years of teaching, the question that the students do the worst on is the types of solid question. And to be fair, it is a lot of information there. There's also a lot of potential combinations that they can give you, so you kind of have to be ready for everything. So that is why kids struggle with that the most. Remember, with this question, the whole aim is to tie back to the particles involved and the bonds that are there, because that's going to explain everything to why they have these certain properties. It does get easier next year and the continuation of this standard for level 3, because it narrows it down just to the covalent molecular solids. But unfortunately for this year, it is a lot. So just be mindful, this is probably the question that I would put at the top of your priority to study, because this one's probably going to be the one that's going to hit you the worst. All right. The nice thing about the polarity and the shape ones is that it has a set structure to how to answer them. So just keep that in mind. All right. Just so you guys are aware of the work that I have set, I'm very mindful we're adding at 50. So I'll show you guys the Mahi choice and the CPR quizzes just so you know what's there for you guys to work on. So for the Mahi choices, there are some SciPep pages that tie onto that. Again, do as much or as little as you guys need to. I just want you guys to do it for comprehension checks. If you feel confident already, go ahead and go into the no break too small, because the best practice you can do for the assessments is to do an exam question. If you can't do an exam question, then go back and do the SciPep pages, because they are more scaffolded. And then lastly, I have put 2 CPR quizzes, one for polarity, one for types of solids, just so you guys have that opportunity to practice it. The answers are on the Google site as well, so you guys can check it. But I do encourage you guys, if you want me to check your work, hand it in, because otherwise I'm not going to see it. I'm not going to go through 20 things all the time to check who's done the work, who hasn't done the work. If you hand it in, then I know you've definitely done your work. All right. Questions, concerns, or comments? No? All right, let me just show you what I got, just so you guys can see. So these are the collated questions. This is the polarity quiz. I had an alarm going, so I know. Don't forget. So you see here, they've given you the Lewis structures. They just want you to ask the polarity and then explain it. So that's a polarity question. This was from the 2020 mock. And then this one here, types of solids. So this one's this is a full exam question, because now you guys have done everything for types of solids. So you see you're categorizing them. They're asking you to explain electrical conductivities. In this case, they picked the metal and the non-metal, which isn't surprising that they've done that. And then for this one here, they talked about solubility, and then what you compare fluorine gas versus magnesium fluoride. So they're good exam questions. Let's use that. All right, cool. So that's us.